Morning, everyone. Welcome to another introduction to astronomy. This one's for April 2022, where we like to pick a topic and have a discussion, in particular introducing various concepts and ideas and principles of astronomy. So, this beautiful image is one of my favorites. You know, you come across beautiful images like this distant galaxy, it might be on the internet or in a book or something. And almost always, like with this galaxy NGC 4526, they quote the distance, how far away it is from us. In this case, 55 million light years away. And you can't help but think, how do these guys know this? How do astronomers measure distances to objects across space and that are so far away? And that's why tonight we're going to commence a two-part session. Part one was this month, and May will be part two, measuring distances in space. It's going to be an introduction to the principles and the methods astronomers use to measure large distances, which will be tonight, part one. And then next month, part two, we're going to be looking at the cosmic distance ladder, which you will learn is a tool they use to optimize accuracy and precision. Because I'm sure at the end of tonight's talk, you might think, how accurate is this? How precise are these? And that's what we'll talk about next month. And I'm going to introduce you to a really cool thing called the Hubble tension and offer a possible solution to that. So let's get moving. So this is tonight, part one, principles and methods. An introduction to the principles of methods astronomers use to measure large distances across space. Okay, so I've split it into three chapters, if you will. One, the units that astronomers use to measure astronomical distances. The second part will be principles and methods that the astronomers use to do these measurements. And then third, I always like to give you sort of three sort of real key messages. I call them sticky messages, for take-home messages that you can recall. So, one, units used to measure astronomical distances. I've split this into the solar system, which means measuring distances to the sun, the moon, and the planets, and then stars and galaxies. So, what do astronomers do for measuring distance to the sun, the moon, and the planets? They use good old basic kilometres, not miles, Americans, but kilometres, metric. So that we're all familiar with. And just to give you some rough ones, nice and easy ones to carry in your back of your mind, always handy to have. The distance, the average distance, I should say, from the Earth to the moon, because, you know, the moon has quite an elliptical, elongated orbit around the Earth. So what they do is they get its average distance. We'll talk more about that later. But its average distance, easy to remember up here, 385,000 kilometres. That's the distance. So it's kilometres they use. And the same from the Earth to the sun. It's roughly about 150 million kilometres. So there's an extension to that. They'll often talk about astronomical units. And that refers to, they've got the distance from the Earth to the sun, 150 million kilometres, thereabouts, and they've labelled that one astronomical unit. And you'll often see that used when they look at the distances between the sun and the other planets. And I often round them up a little bit. It makes things easy to retain. And I've just listed here. Here's some of the sort of decimal points things go on here. But I've made it a little simpler. And here's some easy figures that I use in my head to just like an easy to retain. I think it's just Mars, 1.5 AU. In other words, it's 1.5 times the distance. It's another half AU again. Jupiter is 5 astronomical units away from the sun. Then just double that out to 10 for Saturn, double that again out to 20 to Uranus, and then you just add another 10 on for Neptune. And that's a nice, easy way, just if you memorize that nice little sort of, those figures like that there, they're easy to retain. So if someone sort of says to you something about distance, it's easy to work out. They said, oh, what's roughly, what's the orbit of, say, Saturn? You think, well, that's 10 AU. AU is 150 million kilometres, so you multiply that by 10. Okay, so how about close stars nearby and galaxies nearby? So close stars and galaxies, what do astronomers do about that? They use what they call light years. Now, a light year is the distance that light travels in a year. Light travels at 3 100,000 kilometres per second. That's a blink of an eyelid, does about 6 laps of the Earth. Bang, like that. That's amazing. So they used light years to measure the distance to stars within the Milky Way and also our local group. It's like a little group, a little cluster of galaxies nearby to us. They used light years for that. And just a couple of examples, Proxima Centauri, it's our closest star to our solar system. That's 4.3 light years away. Andromeda Galaxy, that's our nearest large spiral galaxy within our local group, that's 2.5 million light years away. Whenever you see a capital M in front of something, you pronounce that mega, and it means million. So you see that a lot in astronomy. You'll probably see it a few slides later on, and that just means 2.5 mega light years, which means 2.5 million light years. How about stars and galaxies that are beyond our local group, more distance? They tend to use what they call parsecs. A parsec, we're going to talk more about parsecs later on and with parallax, so we'll talk more about that. But a parsec is about 3.26 light years. And they use that sort of measure, if you will, out to distance galaxies and clusters. Now, for example, here, this image here, is the Coma cluster of galaxies, and that's quoted as being 99 megaparsecs, or 99 million parsecs away, which works out to about 321 million light years. So they use something slightly different for the more distant stars and galaxies. So just summarizing that the units that astronomers measure, when talking about the solar system, distance to the sun, the moon and the planets, we tend to use kilometres and astronomical units. When you're looking at distance or close and distant stars and galaxies, you tend to use light years and parsecs. So that's just section 1 in summary. By the way, I'm writing in the throes of finishing up a handout on all of this. And feel free to email me anytime over the next few days. It's an easy one, membership@astronomy.org.nz. membership@astronomy.org.nz, and say, hey, Chris, saw your thing the other day. I'd love it if you could send me a PDF of your handout, which I can do. Hopefully we'll be in person for part 2. We don't know. But if we are, I'll certainly have handouts for both talks. It's nice to have a handout, isn't it? Okay, so let's move on to the second chapter, the principles and methods that astronomers use to measure these big distances across space. There's 5 main principles and methods, which we're going to have a look at. But at trigonometry, God, remember that. That was sort of, 5th form at school? Year 11, I think that is these days. And I'm going to give 3 examples of using trigonometry. Standard candles, I'm going to give 7 examples of that. Spectral redshifts, and it's those 3 are probably the main big ones. But also there's 2 sort of relatively new sort of things on the block, a standard siren and a standard ruler, and we're going to talk about them as well. So let's go on and talk about geometric trigonometry. Brush up on your high school math. Okay, so, and I've split this into 3, laser and radar, parallax, and water megamazes. So laser and radar. Okay, laser reflections to the moon. One of the jobs, one of the really cool things that the Apollo astronauts in the late 60s and the early 70s, what they did do, one of the jobs is they left on the lunar surface these big mirrors. You can see here's a picture of it here next to the lunar module. These nice big mirrors they positioned on the moon facing back towards Earth. And the point was that it enabled scientists on Earth to fire a laser beam to the moon's surface, strike that reflector, and it would bounce back, reflect back to Earth again. And of course, it's light. They know pretty well. I've got the speed of light down sort of pretty accurate measurement. So they just had to time the return distance from Earth return back to the moon again. And that distance, hey, it's easy from there. You just calculate the distance. So you might say, oh, okay, what were the results? And as I mentioned, the moon going around the Earth has quite an elliptical or elongated circuit around. When the moon is at its closest, it's called perigee, when the moon's really big in the sky, its distance is about 360,000 kilometres. And when it's at its furthest distance from Earth, which is known as apogee, that's about 405,000 kilometres. But I don't get bogged down with that just on the top of my head. I just think of the average as 385 kilometres. So that was a pretty cool thing that the astronauts did. So how about this? There's a similar principle of doing that same sort of thing, but to the planets. But this time what they're able to do is get the big radio telescopes, transmit microwaves, that's light and microwave wavelengths, to the surface of the planets. That would bounce back again. And once again, the timing of the return signal would give you the distance to planets. And of course, they're able to do it to the moon, and just to see how accurate it was too, and compare it with the very, very accurate lasers. So they got pretty good at doing radar, and they use radar to reflect off the surfaces of planets. Now, you think, okay, that's pretty straightforward. But here's something interesting. You might say, well, how do they measure the distance to the sun? Well, they use radar reflections to the planets with a bit of your fifth form trigonometry. And here it is here. Okay, here's the sun, here's the Earth. You wait until you see the Venus at its maximum separation from the sun, from our perspective. You get your radar, send your microwave signals to Venus, get it back again, measure the time, and that tells you the distance there. You then draw yourself a right-angled triangle by measuring the angle between the sun, or rather the Earth, rather looking at Venus and us looking towards the sun. So you work out that angle there. And of course, simple trigonometry, you know this distance here, you know this angle, you can work out distance A, and that gives you the distance to the sun. Pretty cool, huh? So that's laser and radar, sort of measuring distances within the solar system. How about this thing about parallax? What's that all about? Well, parallax, this little sort of GIF file here of the little motions, it actually perfectly sums up parallax. Parallax involves observations of objects in the sky from different positions, and once again, a little bit of trigonometry comes out of the woodwork. So it's all about observing a star's position from two angles and allows its distance to be calculated. And what I want to do here is do a little bit of an exercise. So you can do it too, we'll take our time. What I want you to do while you're watching the computer, just do it for me. Hold your finger right up above your nose, next to your nose, but so you can see it between your eyes, like that. Close one eye and just make a note of the object in the back of the room that's in line with your finger. Now, swap eyes. Do you notice that suddenly it's now aligned to another object quite some distance away in the room? That's called parallax. Flicking your eyes backwards and forwards, and you can see my finger or your finger is shifts in its relation to background objects in your room. Okay, so that's one principle, that there's this shift that you can measure just by looking at, observing it, that one object in the one place from a different angle. Now, what I want you to do now is move your finger further out, say to full arm's length, for example. Do that same thing again. Get one eye, close one eye, and then flick eyes over and watch it, look at it through the other eye. Once again, you notice the parallax. That's the background object that lines up with the finger is different again. But what do you notice this time? The angle or the difference in shift is a much less. So that tells you that the further away something is, the less the angle or the shift, the parallax shift that occurs. So that's two important principles. So you've got that idea now. So, okay, here we have the Earth going around the sun. So what the astronomers will do, they'll observe, say, let's pick a month, say June. They'll quietly, and they'll have a look at a star, and they make a note of the background, what stars it's in line with. They'll then wait 6 months and go through to, say, December, and they'll do that same observation of the star again, and they'll make a note of the background stars this time. They're then able to draw this sort of type of diagram up. Since the distance, this distance is equal to this distance, it's the orbit around the sun is roughly the same, it's very close to circular. Able to draw a line to split that angle. They can obviously see that angle there quite happily. They split it in two, and they get what they call the parallax angle. And the parallax angle is the key to all of this. and I'll show you. Okay, so it's the stellar parallax formula is used to determine the distance from the angle. And all it comes down to is the inverse of the parallax angle gives the distance to the star. The distance is always given in parsecs, and the angle is always in rather in arc seconds. Now you might think, ooh, what's an arc second? Well, you know how you got a circle, you got 360 degrees. So you split those down to a degree, and a degree in the sky, you know, is sort of yay big, it's an angle in the sky. Every degree is then divided up further into 60 arc minutes, and then each individual arc minute is split up into 60 arc seconds. So it's a very, very small slither off the sky, and that's called an arc second. So here's the formula here. D for distance in parsecs equals 1 divided by the parallax angle in arcseconds. And remember, 1 parsec is 3.26 light years, a light year being 10 million kilometres. So let's have a go at an example. Sirius, that's the brightest star in the night sky. It's called the dog star, star Canis Major. It's the brightest star in Canis Major. So at the moment, it would just be setting about now. You've got, or just set, Orion, you know, that's sort of with the pot, we call it the pot, but Orion, the hunter with his Orion's belt and the sword hanging down, we see it as the pot. And you go a bit further over to the east and you'll see Canis Major, because every hunter has his dog by his side. So Canis Major, and you'll see the star, bright star in Canis Major, so it's just to the east of Orion, and that's called the dog star. And it's also called Sirius is its proper name. So I picked that out because it's a nice bright star. And so you might say, well, how close is that? So you picture it here in June, and then you wait 6 months and get another angle, and you work out that the angle here is 380 milliarc seconds. That's getting really small. A milliarc second is a thousandth of an arc second. So this is probably illustrating to you the accuracy that these instruments today in astronomers can get down to. And I put the abbreviation MAS. I put that in there because sometimes you pick up an astronomy paper and you'll see something about MAS. It means milliarc seconds, just an abbreviation. So it's essentially 0.38 arc seconds. So you get the inverse of that, 1 divided by 0.38, and that comes to 2.64 parseconds. You know that a parsec is 3.26 light years. So you get your calculator out, and that comes to 2.64 parsecs is 8.6 light years. So next time when you're looking up the sky and you point out Sirius to someone, say, hey, that's 8.6 light years away. And they go, really? Oh, really? That's interesting. Hey, thanks for sharing that. How do you tell? And then you can tell them all about parallax. Now, stellar parallax, it's not surprising, comes at a range limit. What have we just learned? The further away a star or an object, the smaller the angle to measure. And of course, you can only measure anything, let alone an angle, to a certain point, and you're just starting to lose it in terms of your ability to do it accurately. So parallax is best suited for relatively nearby stars. Ground-based measurements, which we just used that as an example, reliable up to about 300 light years, and then the angle's getting a bit fuzzy. Why is it getting a bit fuzzy? One of the reasons is you're looking through the atmosphere, and the atmosphere distorts light, and suddenly you've got all this distortion going on. And that makes life a little bit more difficult for the astronomers. So what do? They put up into space a satellite to do the job for them. There's 3 satellites that have been doing a lot of work up there in that regards to that. Hipparchus, launched in 1989. That's okay up to about 1,600 light years. Hubble Space Telescope can do some of this up to about 10,000 light years. But the Gaia satellite here, that's in space, positioned at L2, Lagrange point 2, in May, we're going to do a whole talk about the James Webb Space Telescope, and that's based up there, and we're going to talk more about L2. So it's up in space there at L2, and that is sole purpose is to really get good positions in space of where stars are, and that's accurate up to about 20,000 light years. It's pretty cool, isn't it, compared with the 300 that astronomers only could do before the space age. 20,000 light years. So that's pretty cool. So that's laser and radar for within the solar system. Parallax for stars, up to about 20,000 light years away. And how about these water megamazes? These are interesting. So, water megamazes are a fairly new tool and really powerful. They're very, very accurate. So let's do a bit of background. It's probably the easiest thing first. Most decent-sized galaxies have at their heart, right in the centre, what they call a supermassive black hole, which is, as the name implies, it's a black hole that's supermassive. The black holes in these galaxies, in the centre of these galaxies, are millions of times the mass of our sun, for example. They are huge, massive black holes. We have one in the centre of our galaxy, the Milky Way. It's about sort of a little over 6 million solar masses. They can get actually up to billions of solar masses, some of these really big, massive, big ones. And these supermassive black holes, if the galaxy is known to be what they call active, it means there's a big accretion disk. Black holes tend to form accretion disks full of all sorts of gas and dust and molecules and materials going round and round this disk like that. And in the inner part of the disk, the materials start falling in like that, creating huge amounts of energy as sort of gravitational energy is being released. That, by the way, the release of gravitational energy is far more powerful than nuclear energy. Very, very powerful. You get these powerful jets, you know, shooting out either way. But nevertheless, to say this is a pretty dynamic, highly energetic environment, this disk. And in these disks, you'll often get little regions high in water. And then you'll get some sort of high energy event or something, whether it be a high energy X-rays or a shock wave going through it. And that will stimulate the water to emit really intense microwave wavelength light. And they call it masers. And its sort of analogy would be lasers that we use, sort of light amplitude stimulated emission radiation. Well, this time it's microwave instead of light in optical or visual wavelengths. It's in microwave wavelengths. So they call them masers. And what they're able to, the astronomers, they use the VLBI. That stands for the Very Large Baseline Interferometer. And that's about 10 big radio telescopes scattered around the globe. And they work in unison. They all look at the same object and they bring all their data together, and the computers munch the data up and recreate an image with massive resolution as if all those 10 around the globe were one massive big telescope, the size of the array. They call it array, but you get a whole stack of telescopes all spread out like that. So, and that's called interferometry. So they've now got this, and they can focus in particular one galaxy in particular has proved to be very, very useful, NGC 4258. And its quote has been about 23.7 million light years away. So they were able to measure and track about 30 of these masers, these air regions, highly energetic regions of water, they're emitting intense microwave wavelength lights at different locations within the disk. And they're able to monitor, measure them, and track them and make note. And of course, they'd go back and do it every few months to get an idea of what they call the angular velocity, or the way that things are moving around within the disk. In fact, I think here is that arrow. I don't know if I got no, it's not. I thought I might be able to get an arrow going in here, or a pointer or something. I don't know if you can see it, but around this disk here, I'm just going to quickly pen laser pointer. Aha, that's probably better. I should have done it earlier on. Okay, so you got this disk, and you got everything going around and round in the disk. And you got these masers going round and round in here as well. They're able to track those and make a record of them. Meanwhile, back in the laboratory, their supercomputer, they know the mass of the supermassive black hole. They're able to work out the sort of the size and the dynamics that are going on in the disk. And the computer gives them a model of what the angular velocities should really be like, as if you're right up there close, what they call the absolute values of those angular velocities. They then compare and contrast the observed angular velocities after many months of recording with those computer-based ones around models of what would normally happen within a disk. And they use a formula to compare the two angles, angular velocities, and from there they use a formula to work out the disk. That's rather the distance to that disk, which infers the galaxy. And to give you an idea is that things further away give a narrower angle. And a good example of that is looking at, say, an aeroplane up in the air. An aeroplane going close by, you see it go like that. An aeroplane further away is going a lot slower. So the angular velocity does change. So that's sort of a fairly new and very powerful tool that they're using. And it's used with trigonometry and geometric calculations. It's high-tech sort of supercomputer material. Okay, so that's the 3 geometric trigonometry methods. Let's move on to standard candles, and we'll have 6 examples here. So first of all, what are standard candles? Well, a standard candle in astronomy is an object of known brightness. If you get anything where that shines light, and you know exactly, because you understand the process that's going on there, you know exactly how bright it actually is. And it's called a standard candle. Cepheid variable stars and type 1a supernova are the common ones that are commonly used and you often hear being talked about. So the idea is that you observe you make a note of the brightness something appears to, the observed brightness, and then you compare it with the true brightness, and that allows you to work out the distance. You might say, well, how do they do that? Well, they use what they call the inverse square law, which is 1 over R2, or D2 if you will, R or D they use for distance, and it describes the way light spreads out across space. So here's S for source, light spreading out like that to a set distance. And if you double the distance, the brightness of the light will be 1 over 2 to the power of 2. In other words, 1/4 the brightness. If you go out a third, of course, light's spreading out more and more. You can see here, like 1 patch here suddenly has to do 4 patches here. If you go out to 3 times the distance, the light has to spread out over 9 times the area. So the light's going to be as 9th as bright, or 9 times dimmer, whichever way you want to look at it. So that's why they use the inverse square law, and that's essentially how they do it. You know how bright an object is, you measure how it looks bright, how bright it looks from Earth, and use the inverse square law, and you can easily from there work out its distance. Now, you might say, well, how about astronomers? Don't they use the word magnitude as a measure of brightness? And yeah, they do. And you might say, isn't the magnitude logarithmic? Absolutely. So how do they handle that? They have an equation called the distance modulus equation, and allows for the logarithmic nature of magnitudes. And here it is here. I'm not going to go into depth. That's another whole talk. But little m is usually the observed or the apparent magnitude of a star when you look through your telescope. Capital N usually refers to its absolute magnitude. And then you put the R in there for your distance. And then you know this. That's from your telescope. You know this from your theory, your standard candle, and from there you put those into the equation, and it's very easy to work out what R or D the distance is. And distances are calculated in parsecs, by the way, too, for this equation as well, just like with parallax. See, parsecs is quite handy. So now we've got 6 examples here of standard candles. The list is by no exhaustive, but these are sort of 6 ones that you often see. So first of all, Cepheid and RR Lyrae variable stars. So what are they all about? Well, that they are a type of stars that pulsate. They're called variable stars for that reason. They pulsate, but they pulsate at regular intervals. So instead of being, all over the place, they just pulsate at regular intervals. And the rate at which they pulsate, or the period of pulsation, if you will, correlates exactly with their absolute luminosity or brightness. And so you just simply measure the regular intervals, their period, and here's the nice little graph here, and that matches straight up with, you can determine exactly how bright they are, their absolute brightness. Now, so we put here, split it into 3 groups. Here's the Cepheids here, and the Cepheids come in 2 types. Type 1, which are relatively young stars, high metallicity. High metallicity means, with astronomy, the composition of stars, you've got hydrogen and helium, and anything heavier, elements heavier than that, lithium and carbon and so on, and iron, that they're all called metals. Anything heavier than iron and helium. And of course, the very first stars after the Big Bang were just, all they were hydrogen and helium. But heavier elements are made inside stars. Stars then go supernova eventually at the end of their lives and spew out all those metals and incorporate it into the next generation of stars. So it follows that each generation of stars gets more and more metals in them, or high metallicity is what they call it. So you've got type 1 or classical Cepheids, and then you've got type 2. So the type 1s are much younger, so they're sort of a few generations on, so they've got high metal content. Then you've got type 2 Cepheids, and they tend to be older stars and of lower metallicity. And as you can see here, for a given period for their cycle, they're that little bit dimmer. But it's really important. The reason I mention this, it's really important that you know when you're looking at a star, if you're looking at a type 1 or type 2. Dear old Edward Hubble, when he first was trying to work out the distance to Andromeda Galaxy, he was looking at Cepheid variables to do this, which is a good idea. But in those days, they didn't know there were actually two different types, and he got them muddled up, and that threw his calculations right at his figures. His principle was bang on, and that's why he became famous, but his actual figures were out because he didn't realize that. And you might think, well, I know that now. I'll go out and have a look at them. It's not that straightforward sometimes. It can be deceiving. And that's one, as we'll explain shortly, is one of the disadvantages of using Cepheid variables. So those are the two types of Cepheid variables. And then the RR Lyrae are older stars again, quite much dimmer down here, and they are once again, because they're older, low metallicity. Okay, so that's one way you look at these stars and you see how often they pulsate, and you work out how bright they are, or rather, how bright the luminosity. So I put this in here just to show you, some of you might be thinking, well, where do they fit on the Hertzsprung-Russell diagram? And if you're sort of relatively new here, the Hertzsprung diagram, almost every time you'll hear it, there's a whole talk we got on it. And it's just a diagram that you show the luminosity or brightness down the y-axis, and it's a function of the temperature of a star. Stars spend 90% of their time in a nice stable state, burning hydrogen in their core into helium. It's called the main sequence, and that runs up here from the really cool stars here, cool dim stars, and it runs up vertically in a nice, sort of rather diagonally, I should say, up to more brighter and hotter stars. And then stars, when they run out of hydrogen, they move what they call move off the main sequence, and they become red giants and go across this way up here, go up what they call the red giant branch, and then come back across a horizontal. That's going to be relevant shortly. And there's a strip through here called the instability strip. And it's the sweet spot, if you will, where the conditions in the star are just right. And we're going to talk about that shortly, what those conditions are. The conditions are just right to create these pulsations in and out, depending on the luminosity of the star. And you see your classical Cepheids are up here, these big bright. They're actually from supergiants, these ones, the big classical type 1 Cepheids. And the type 2 Cepheids are down here, red giants. And there's your RR Lyrae stars there. So I think I pretty much summarised that all here. Cepheids, your highly luminous post-main sequence giants and supergiants. The type 1s are the big bright ones. They're the red supergiants sitting up here. The type 2, less bright, sort of older, low metal stars, population 2s, and these are red giants. And then your RR Lyrae stars are also red giants, but they're older red giants. Okay, yeah, so what's going on under the hood inside these Cepheids and RR Lyrae? It's called the Kebab Mechanism, and it goes right across all three types of stars. Three principles. We're going to talk about that shortly. Ionization, how that makes something opaque to light. The concept of recombination and how it makes something transparent to light. We're going to have a look at the stellar interior zones, and then we're going to bring all that together and show you how all that acts like a thermodynamic piston type engine. So let's do that now. So the whole principle of ionization. So as you probably recall from high school days, atoms have a central nucleus. They're positively charged and they have negatively charged electrons around them. And they are bound together by electromagnetic forces. And they're happy in that position. And conditions on Earth around us, everything's as a normal neutral atom. But if you start heating up that environment and make it more energetically, suddenly starts moving apart, and the energy is such that the electrons and the negative electrons and the positive neutrons go their own way, and you've just got a big soup or a sea of atomic nuclei and electrons just all running amok. And in here they've got hydrogen. We've got hydrogen nuclei here, which is a proton, and helium nuclei here. Why? Because that's the main constituent of stars, hydrogen and helium. So you've got this big hot state here. We've got all these electrons and positive nuclei here all running amok, and you put a light beam through here, and the light just starts interacting, particularly with the electrons, and it just bounces backwards and forwards all over the place, the light. And it can't get out the other side, or very little does. So it's called opaque. A hot ionized region is opaque to light. In the same vein, if you allow that system to cool down and allow the negative electrons to link back up with the positive atomic nuclei, they all becomes neutral again, and light can travel through unimpeded, not interacting with anything, and you call that region transparent. That process is called recombination, when atomic nuclei get back together again. They make up. So let's put this now in the context of what's going on inside stars. So when you get a star, the inner core and the inner regions of the star is really hot. So the material is ionized. The electrons have been pulled out, and the electrons and the atomic nuclei, hydrogen, helium, are just running amok, rocking and rolling, totally independent of each other, having a ball. And of course, that region is opaque to light. To the other extreme, you go to the outside part of the stars, where it's cooler, so a lot of the electrons have joined back up again. The electrons and the positive atomic nuclei have made friends again, and all hooked up again. So that tends to be transparent. Now, in stars, these particular giants and supergiants, with a surface temperature of 5,500 Kelvin out to about 7,500 Kelvin degrees, that's their sweet zone. If that's it, they have a sweet spot in the middle called a partially ionized helium zone. That's partially ionized. So it lets a little bit of light through, but it's also partially opaque. Now there's a cycle. Let's start the cycle off when the star's shrunk down. So if a star is shrunk down, this zone, this sort of sweet spot within the star of sort of partially ionized helium, has suddenly shrunk closer. So it's got to the hotter region of the star. So what's going to happen? It's going to become more ionized, and all the electrons are going to be buzzing around, running amok to the atomic nuclei. So what does that mean? It's going to become opaque to light, and of course light is heat. So what happens is that the heat builds up, and here what happens is it starts to expand, and it starts pushing that ionization zone further out. The whole star's puffing out because it's opaque, it can't give in. But what happens as something starts to expand? It cools off as well. So it slowly starts to cool off as it expands. What happens when it cools off? It recombination. You get the atoms, the electrons joining back up to the atomic nuclei. What happens then with recombination? It becomes transparent again. So all the light and heat can escape back out again. So the whole star cools back down when the heat escapes, and it goes back this way. And it's a cycle of being opaque, heating up, expanding, swelling, then cooling down, allowing all the heat to escape, and then shrinking back down again, goes backwards and forwards. So it really acts like a piston. It's called a thermodynamic engine, and it's acting like the piston. And that is the mechanism behind these red giants and red supergiants, Cepheid variables, and these RR Lyrae stars called the Kebab mechanism on that instability strip in the Hertzsprung-Russell diagram. Okay, I put this slide in just really to show you the sweet spot. It sits here between 5,500 degrees and 7,500, where you get this helium, hit this zone of ionized helium here that could just go up and down the right amounts. Temperatures are too hot, the helium tends to get pushed further out, and you tend not to get that sort of fluctuation piston effect. And similarly, if you get it too cool as well, you just lose that effect. So that's the sweet spot in there. And that's why you've just got that narrow strip on the Hertzsprung-Russell diagram. Yeah, there you got that little strip there of the right temperatures. Okay, so let's look at some of the advantages. So why use Cepheid variable stars to measure differences? They're extremely bright. How bright something is, they call it luminosity, and they use the sun or the sol brightness as a standard. So one solar luminosity is the brightness of our sun, power output. The classical Cepheid variables, that's your type 1, are really bright. They're 100,000 times brighter now sun. So that tells you, you see them at big distances. You can see them, the Hubble Space Telescope can see them out to about 50 million parsecs. How crazy is that? So that's what that's about 160, 170 million light years away. How about disadvantages? To measure the pulsation periods, you've got to do multiple observations. You can't just get one observation because you want to plot its brightness at what they call a light curve. You want to see it go up, 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 and see where it peaks, watch it down, see how low it gets, and try and get some sort of pattern going on there. And of course, that takes multiple recordings. Every time you do an observation and a recording, errors sneak in. So this is very much dependent upon multiple observations. That is a potential source of errors sneaking into your data. The other thing is there's relatively rare supergiants, and there's a thing called the initial mass function of stars, where nature has a bias for producing more and more little stars. It's almost like a pyramid, if you will. You've got fewer big stars, and OB stars, these are the big massive stars. There's very, very few of those. They're relatively rare. And as you go right down the sort of pyramid, it's an exponential one too. You got so many more little red dwarf stars for every one O and B star. So these Cepheid variables are supergiants from the most massive stars called O and B stars, but they're very, very rare. So you've got to hunt for them. As I mentioned earlier on, there's two types, type 1 and type 2. You've got to be certain you're dealing with a type 1. It's not always that clear. The other thing is these are observed best in visual wavelengths. And visual wavelengths can get dampened down. The luminosity can get dampened down if there's a lot of dust between you and the star. And it's called extinction is the technical term for it. It means that the light tends to get dimmer because obviously you're obstructing some of the light, and it gets a little bit more reddened. It's like the principle of sunset. Light's coming towards you, hit some dust, the blue light gets scattered, and it's the red light that has a bias for coming through, just like you have a sunset and a sunrise on Earth, same principle. So it's got some, so that's going to upset your data too. So wonderful stars to look at, nice and bright from large distances, but they're not without their problems and their errors in the data. So that's Cepheid and variable stars. How about these detached eclipsing binaries? What are they all about? Well, binary stars refers to when you get two stars gravitationally bound going round and round each other. And eclipsing binary stars, meaning that the rotation round each other is in our line of sight such that one blocks the other one on a regular basis. So that's what an eclipsing binary star system is about. Detached refers to the fact there's no transfer of mass going on between the two of them, because often you do, if you get one really big star, it'll often siphon material onto another star. So they're fully detached. And you can do a light curve. As one goes in front of the other one, you tend to get a dip in the intensity of light, just like you see here. So studying these light curves will give you an idea of the size of these stars and also the periods, how long they take to go around one another. That provides you a lot of important information about the mass of the stars. Also, you get your spectroscope out and you look how fast they're going around, but also you're able to measure the temperature of these stars. If you know the mass of a star and you know the temperature of a star, you can then work out how bright it is. It's sort of mathematical equations, pretty straightforward sort of stuff. So detached eclipsing binaries allows you to work out the absolute magnitude of stars, and once again you compare it with your observed magnitudes. Star cluster main sequence fitting. Okay, this is where you get a cluster of stars. And a cluster of stars refers to a big bunch of stars in the sky, all closely together, that are all the same age and formed from the same molecular gas cloud that's collapsed to form all these stars, as stars do. And they're all for roughly the same distance from one another, so you can do this. And you map here, it's called a colour magnitude diagram, and whereby you map how bright something is through your filter up on the y-axis, and on the x-axis, use what they call with some filters the difference between two filters, and it's called the color index, and it reflects the surface temperature of a star. And you plot in a star cluster all the stars, and here all these main sequence stars all going up nicely up here. And this is the star cluster Hyades. And Hyades has been well studied with parallax method, because it's fairly close. They're able to tell you the distance of these stars as well. So what they do, you put something like Hyades up here plotted up, then you get another star cluster. In this case, they've used Pleiades. And they've mapped this onto the same colour magnitude diagram. They've fitted it in. But look, it's parallel, as you'd expect it to be, but different values. And what you do is you get some stars and say for a given temperature, let's say just pick out 6,000 degrees. So you're 6,000 degrees for a given star in Hyades at that temperature. Notice it's sort of so bright, so it's 1 point, say, sort of, well, probably 2 or 3, because that's logarithmic. It's probably 2 or 3 solar luminosities. But look here with Pleiades, for that same temperature, it's a lot dimmer. It's the same type of star, the same surface temperature. So they should be, in theory, very similar brightness, but it's not. Pleiades stars for each given temperature is a lot dimmer than Hyades. What does that tell you? It's a lot further away. So once again, there's formulas to do that. You know the distance to the stars in the Hyades for a given temperature through comparing with parallax measures. You're able to get a formula out and work out the distance to the stars in Pleiades and get the average distance, and that will give you the distance to the whole cluster. So that's one method that you see used not uncommonly. Tip of the red giant branch. This is a really cool one. So a little bit of background. So as we've been talking about, stars spend 90% of their time in the main sequence burning hydrogen in a nice stable state, burning it into helium. But 9/10 of the way through their life, they run out of hydrogen in the core. So what happens is helium builds up in the core. And with helium, the temperature starts rising, but also you start getting some hydrogen fusion in the shell around it, and the star swells up and starts appearing redder and bigger. And it's what they call a red giant. And if you do a color magnitude of that, let's just go back a little bit here. So as the star swells up, the pressure comes more and more because hydrogen fusion in the core is stopped. And of course, that's the main thing, propping the star up. So the gravity is bringing all the pressure down. The pressure rises higher and higher in the helium core. And the temperature gets higher and higher with that until it reaches a critical temperature and a critical astrophysical state. And then helium fusion can then kick in. For stars from 0.4 to 1.8 solar masses, they're in a cores because of all this pressure going on. They get what they call a degenerative state builds up. And it's a particular set of circumstances whereby exact pressure and temperature, helium ignites very quickly, and you get a rapid runaway effect of just helium fusion all starting up through the core. And they call it a helium flash because it is. It's not a flash from the outside. You don't see it from the outside of the star. But if you're in there, imagine and looking at the core of the star, you see a big flash. So they call it the helium flash. So that's a little bit of background in there. Stars greater than 1.8 solar masses tend to kick in a little bit slower. They lack that little bit of sort of that real high luminosity helium flash. So if you get a cluster of stars, or even a whole stack in an open cluster perhaps, or in a galaxy, collection of stars in a galaxy, and each individual star you plot in a color magnitude diagram, your magnitude or how bright things are, and your color or your temperature here. Here's your main sequence of stars you'll get, and these will be your stars, your red giants. They start getting a bit cooler, and then they start getting brighter and brighter as the star starts to swell. And all the stars to get to a certain point up to 1.8 solar masses, and then you get that runaway instant helium flash. They understand the astrophysics processes that are going on, where it's very much a standard luminosity that the stars undergo. And you might say, I've written here the I band. The I band refers to light in the near infrared, just below the visible light. And they typically like to look at these stars and the red giants in that I band, and it's pretty standard luminosity. They'll all be roughly in that I band, in the near infrared, a magnitude of about minus 4.0. So if you plot out a few thousand stars and you see them all accumulating, you start seeing a whole group of them up here, you know that in your I band, that's about the absolute luminosity is about a magnitude about minus 4.0. And of course, you see what you observe it as in your color magnitude diagram. And once again, you use your distance modulus formula for working out the distance. Now, so like all things, there's pluses and minuses. The disadvantages, they're not as bright. These red giants are not as bright as the classical Cepheid. So you can only use them out to about 20 million parsecs, which is what, so it's probably about 70 million light years. But that's still a reasonable distance, but they're just not as bright as those big classical Cepheids. But there's a lot of advantages. The astrophysical process going inside them is well understood and well standardized. So that's a pretty reliable, that sort of absolute luminosity in the I band of about -4 there is pretty absolute. You only need one single observation of that star cluster to get all your data. Remember we talked about Cepheid, you've got to get a whole series over time, over many days and weeks and months to get a decent light curve, which errors creep into. So you only have to take one shot of that galaxy or that cluster and measure the brightness of all those stars in that. The other thing is they're highly visible in the I band, that the near infrared, which means you don't get the extinction. Infrared wavelengths go straight through. They're not interfered by dust. It's the visual wavelength light that gets interfered, that you get the dimming and the reddening effect from dust. So it's independent of dust between you and the stars that the problem you see for variables. The other thing, remember Cepheid variables, if you get it wrong with your metallicity, your metal content in the star, you can get your data thrown out. The luminosity in the near infrared is insensitive. It's independent of the metal content of the star. So once again, that's another big advantage of using the tip of the red giant branch. So that's pretty cool. That's something a little bit different, another way of doing it. So let's look at another couple of methods, the Tully-Fisher and Faber-Jackson relations. The bottom line is these are two methods to work out the distance to faraway galaxies, both spiral and elliptical galaxies. And what they do is with a spiral galaxy, they try and measure the speed at which stars rotate around the center of the galaxy. And they're able to do it with the spectroscopy. If the star's coming towards you, its light spectra is going to be blue shifted. Another whole talk. Jonathan covered it quite well, and we'll talk more about that next month. But if stars are going away from you, the wavelengths are being sort of red shifted. It's called the Doppler effect. So what happens is your emission lines, spectral emission lines, tend to increase in width, because instead of being a single line here, this case, something's getting, well, here it is, here's the stars coming towards you, they've got the straight arrows, so your lines are getting blue shifted here, further away they're getting red shifted as the stars move away. So they're able to do spectroscopy from that, and they found then, comparing that with checking out the brightness of close by galaxies, they worked out there's a nice little relationship. Here's the rotation rate, here's all the stars going around, so they can determine the rate at which they go around with spectroscopy. And once they work out the rotation rate, they're able to preformed, from the previous tests, they're able to look it up on a graph with a formula and tell you how bright that spiral galaxy really is. Its absolute brightness. Compare that with your observed brightness, use your formula, you can tell the distance to it. How about with elliptical galaxies? They're a whole different kettle of fish. You know how your spiral galaxies, the stars are going around in a nice orderly fashion. With elliptical galaxies, the stars are just running amok. They're running in all over the place in different angles and sort of a lot more chaotic sort of movement. So astronomers do what they measure velocity dispersion, which is the spread of velocities from the slower velocities to the faster velocities in the center. They get this little central part of the most bright part of the elliptical galaxy here. And then they measure the spread of velocities. And that is apparent by how broadened the emission lines get spread out. And once again, as illustrated on this graph here, that correlates quite nicely with the intrinsic or the absolute brightness of that elliptical galaxy. Once again, you then compare that with the observed galaxy brightness, and there you go, you know the distance to that elliptical galaxy. It's called the Faber-Jackson relation. So now the sort of the last example of the standard candles, the type 1a supernova. These are very, very bright events. These, you thought Cepheid variables could be seen from a long, long distance. Well, these are 500 times the distance that you can see them at. They're just extremely bright. You've probably heard of supernova explosions. Out of all of them, these type 1a supernova explosions are thermonuclear explosions. They are the brightest of the lot. And you'll probably recall this was the picture I used in my early slides, my slide 2. And it shows here a faraway galaxy, 55 million light years away. Look at this. That's a type 1a supernova going off in it. How bright is it? It outshines the host galaxy. So the very, very bright transient events, you can tell the distance, you can see them at 500 times the distance of these classical Cepheid variables. So what's going on here? So you got a binary system. One of the members of that binary system is a white dwarf. It's a small, compact stellar corpse from a star up to about 8 solar masses from its main sequence days. So it shrinks down there, and then it's in a binary system with a large red giant. And mass from the red giant gets siphoned off, and you can see that here. Here's your big red giant. Here's your little wee compact white dwarf star. White dwarf star, they're happy. They're stable little souls if they're allowed to keep below about 1.4 solar masses. But if they get up to 1.4 or greater solar masses, they become unstable, and they just explode and rip themselves apart. And that's what's going on here. Mass is accumulating up. Nice little accretion disk going on here, and the material's falling onto the surface of the white dwarf. Suddenly reaches this critical value, and there's a massive explosion. You know, this is 20 days after the explosion. So that's what's going on there. So the astrophysical processes that are going on are well understood. And that's why astronomers are pretty certain they know the absolute brightness, luminosity, of when a white dwarf explodes like this, because it's the same conditions, the same critical mass, same conditions. So they're called standard candles, and you use the magnitude when you look at a supernova type 1a, you then compare it where you know how absolute it is because they're all the same. You compare it with your observed one. Once again, you use your basic formula and you can work out the distance to it. So that's type 1a supernova. So that's it. We've done trigonometry. We've done your 6 standard candles. Let's look at spectral redshifts. And the idea here is this: when light leaves a galaxy, it looks something like this here. You've got nice little spectral lines, and they're at their set sort of positions where they are according to the wavelength of the light, and they're measured up and documented in the laboratory where certain emission lines should be. So the galaxy emits the light like this, but these faraway galaxies, while the light's been traveling to us, the galaxy's been expanding. And of course, the light's busy traveling through the universe as it's expanding, so the light's getting stretched out. And because it's going away from us with the Doppler effect, it's getting stretched out to what they call the red part, or the longer wavelengths of the spectrum where the red wavelengths tend to sit. So it's called redshifting. So all the spectral lines get shifted over towards the longer wavelengths of the reds in the colour spectrum. And that is due to the expansion of the universe. It's called cosmic spectral redshifting. You might go, well, that's interesting, isn't it? Thanks for telling me that. But how do you get the distance from that? Well, there's a formula here. And if you get the observed wavelength, that's these ones here, and make a note of that, there's an equation. You then get the wavelength that you get from the laboratory on Earth, so it's absolute wavelength. V refers to the velocity, the recessional velocity. C refers to the speed of light. So we know what C is, the speed of light. You can observe this. You know what this wavelength is from your laboratory measurements on Earth. So it tells you V, or the recessional velocity, how fast that galaxy is in your telescope, how fast away it's moving away from you. What's recessional velocity? You might go, okay, that makes sense, but I still don't know how you work out the distance. Aha, Hubble's law. Edwin Hubble, when he was sort of looking at these galaxies way back in the late 20s, early 1930s, he then plotted the recessional velocity from a spectroscopy. He used some figures from a guy, Vesto Slipher, as well. And Jonathan talked about this last month in his talk. So they plotted that against the known distance of these close ones. He was dealing with distances way down here. And he noticed that was a lovely straight line. There's a nice linear correlation between the recessional velocity and actually how far a galaxy is away. So he formulated Hubble's law. The recessional velocity equals the Hubble constant. He named it the constant after himself, just I can understand that. Hubble's constant is known as capital H times d, the distance. So if you know v, you can work out v divided by h equals d, and that's how you work out the distance using Hubble's law. So how about a standard siren? Sirens are sound waves, aren't they? So gravitational waves. Gravitational waves is something, new. Einstein predicted them about 100 odd years ago, but it was sort of only been the last sort of 6 or 7 years that we've been seeing them, and that they've been the gravitational wave detectors have been reporting them. And what gravitational waves are from is you get two compact stars in a binary system, neutron star and another neutron star, two black holes, two neutron stars, or one of each. But the bottom line is, that's a little bit irrelevant. They're going around one another like this, and they start getting pulled into one another, get spiraling closer and closer and closer, and they eventually merge. And in the lead up to that merge, you've got huge amounts of energy going on, and that crunches up, those sort of energy being dissipated, creates these waves in the fabric of space-time. And these waves then spread out, and we can pick them up. Billions of years and billions of light years later, we can pick them up and detect them with our detectors on Earth. And they study the frequency and the amplitude or strength of these waveforms that we detect. And from there, they can tell you the masses of the neutron stars or the black holes, and the most likely sort of the byproduct of the merger. But if they know then from the observed measurements, particularly of the frequency and the strength, they can actually work out what's going on, and that tells them that the amplitude or the loudness of what the absolute amplitude of what did actually occur all those billions of years ago. So they've got an absolute magnitude. They compare that with the amplitude that they're measuring back here on Earth, billions of light years away and billions of years later. They're able to compare the two and work out the distance. Once again, using our old friend, the inverse square rule, 1 over r squared. It's the same principle. The waves, the dissipation of the energy fans out like that in the same fashion that light does. And just as light gets dimmer and dimmer, the amplitude or the strength, if you will, of these gravitational waves do the same. So they're able to study the frequency, work out the mass, from the masses, work out the amplitude of what actually did go on. So they're called standard sirens. So for obvious reasons, that's something new that's on the block since since we've only been doing it for about 7 years. So how about the standard ruler? And this is another one that's sort of fairly new. A little bit of background. After the Big Bang, when the universe was formed, the universe was in a hot, dense state, a big soup, if you will, of ionized material. And remember, we talked about this with the Cepheid variable stars. You get ionizations where it's so energetic, the electrons are pulled away from the positive atomic nuclei, the hydrogen and the helium, and they're all just running amok. Poor old light, radiation, doesn't get a chance, doesn't get a show in here, because it just bounces around interacting electron to electron. So the universe was opaque. But the universe was busy expanding, and at about the time of about 300, when it was about 380,000 years old, the universe was cool enough where recombination occurred, where the electrons rejoined back up again with the positive atomic nuclei. So what happened? Light could travel freely. The universe was, it was transparent. And the first rays of light can be seen. We're bathing in them right now. They're all around us. They just percolate, they just permeate right throughout all of the universe. We're bathing in them. And 3 satellites have studied them. Your Kebab, then there was NASA's WMAP, and more recent years is the European Planck satellite. And it's with a lot of precision, it's mapped and found these little minute little sort of detail in here of fluctuations in temperature. And that reflects, those little abnormalities reflect subtle circular patterns in the cosmic microwave background that reflect the early arrangements of matter at that stage when the universe was 380,000 years old. There was a little circular arrangement. They call them baryonic acoustic isolations, which we'll talk about one talk that is a whole talk on its own. And they sort of waves that then spread out. And the relevance is that these little circular patterns resulted in the formation of the matter, or the formation of galaxies. So you get patterns of the patterns of galaxies. And as the universe continued to expand, so did these little patterns, or these little circular patterns, of the arrangement of galaxies. You can see it here. Here's the little microwave, little circular patterns, these baryonic acoustic waves. They spread out, and let's go to here. So they put all this into their computers, the supercomputers, and there's a model called the Lambda cold dark matter model, and it's sort of, they put in the laws of physics. They put in Lambda, that's the cosmological constant of expansion of the universe. They put in dark matter. These are whole new talks, so don't get too bogged down with this right now. But they put in the cosmological model of how they think the universe evolved. And they run it forward and looking and sort of extrapolating those little circular patterns of matter that go up to make galaxies from the cosmic microwave background, run them through, say, roughly 13.8 billion years. And their models suggested that you should get these little circular patterns like this, if you look into the universe, and whereby the average distance between galaxies is about 150 megaparsecs, or 500 million light years. And you know what? Lo and behold, that's what they're up there now. There's a lot of research going on, the dark energy survey and so on. There's been a lot of research into it, and all the data to date with their big sky surveys, their deep surveys, are showing the evidence suggests that, yep, that's exactly what they're seeing. Statistically, you're seeing these big circular patterns of the average distance between galaxies of about 150 megaparsecs. So suddenly you've got the microwave background little circles here, these ones up here, and what happened between here and here, of course, space was expanding. So you should be able to extrapolate with your models of the universe. You should be able to know the rate at which these circles expanded. Well, you should do, because it got to where things look today. So if they are able to measure, well, you're looking back, this shows that quite nicely here. So if you look back deep into space and you see arrangement of galaxies and you measure the average separation of this sort of circular pattern, measure it, you compare that, put that into your computer, compare it with the size here from the cosmic microwave background and the size of today of 150 megaparsecs, you can work out when that occurred in the expansion, evolutionary expansion of the universe, which in terms, when you're looking back through time, you're looking back through distance, same vice versa. Distance and time are all tied in with the evolution of the universe. So you can tell the distance. So they call that a standard ruler, these sort of baryonic acoustic waves. So there you go. There's another sort of method that you can start using. Okay, so that's the principles and the method summary. So we've done your geometric trigonometry, your laser, your radar for the solar system, parallax for sort of nearby stars, water mazes. You can go up to a few million to galaxies, those active galaxies there with accretion disks. Standard candles, which are comparing observed and absolute brightness of objects. Cepheid variable stars and your supernovae 1A are probably the more commonly used one there. And spectral redshifts, which is as the universe expanded, these spectral lines from the faraway galaxies have been stretched off to the red. And I've put little asterisks here. Those are probably the three key ones that you're commonly used. Historically, we'll probably start seeing more of these ones with time as they get better at it, but standard Sirens with the comparing the amplitude of these gravitational waves, and the standard ruler looking at these sort of this, going back and looking at the size of the statistical arrangement of galaxies looking back through time. So that's sort of in a nutshell there. So let's move on to our three sticky take-home messages. 1, distances to solar system objects are measured in kilometres and astronomical units. 1 astronomical unit is the distance from the Earth to the Sun. 2, distances to the stars in the Milky Way are measured in light years, and galaxies tend to be measured in parsecs. 1 parsec is 3.26 light years. Take-home message 3 is trigonometry, standard candles, and spectral redshifts are the main principles behind the methods. We're going to see those later to come, sort of probably in future years. So thank you. I hope you've enjoyed measuring distances in space, principles and methods. And I'm just going to make a little plug. So we've done that this month. Next month, what to look forward to, I'm going to introduce the concept of the cosmic distance ladder. Because you think, okay, these guys are doing these different measures. How can they fit in? How do they know how accurate they are and how precise these measurements are? And the astronomers use a tool sort of merging all these different methods together with some overlap to use a tool called the cosmic distance ladder to ensure their accuracy. And I want to introduce that next month. And I'm going to introduce the concept of the Hubble tension, whereby it's a big problem in cosmology, measuring the expansion of the universe, how the measurements taken from different methods aren't matching up. And I've got a solution to that, a possible solution. And we're going to review a lot of what we did today as well to bring it all together nicely for you. So I hope to see you all next month. So thank you very much, guys. Steve, any questions out there?
We do have a few questions. Thanks, Chris. First question is from Kevin. And he says, did having the mirror, and I think he means the reflector, improve our understanding of the changes in the moon's orbit over time?
Yes. Was it Kevin? Good question, Kevin. Absolutely. Not only give good measurements, but yeah, the moon is slowly receding away from the Earth, and it's all to do with tidal sort of conservation of angular momentum, and the Earth, the tides of the Earth are pulling the moon forward, which is pushing out to a slightly higher orbit. And they were aware of that, and they weren't too sure the exact amount, but it's given them an exact amount, and don't quote me on this, it's something like about 3.2 centimetres per year. You might need to look that one up, so don't quote me on that, but it's that sort of order. It's like 2 or 3 centimetres. 3.2 is a figure I remember, but I might be wrong. So it's about that sort of order that the moon slowly, year by year, is receding away from the Earth. And the Earth, by the way, to conserve angular momentum, is slowing down. You've got the Earth here, you've got a nice big tidal wave, to a sort of a total bulge between the moon and the Earth. The moon's here. You notice the full moons always lag behind the high tides. So the tide is dragging with gravity, dragging the moon forward, and as something moves forward, it tends to go into a further outer orbit. Meanwhile, the moon's pulling back on that tide, which is slowing down the rotation of the Earth. So and that's that they understood the theory of that for some years, and they speculated on probably the measurements, but it enabled to tell them how the distance is changing over time. Great question, Kevin.
Thanks for that, Chris. And a comment and question from Keith. He says, I remember we used to use grazing occultations to monitor the moon's movements. Does anyone do that anymore?
I don't know, Keith. A good question. I don't really know. I suppose now I've got the laser. I don't know how even long ago they did that. So I don't know. Good question.
A few more. Craig wants to know, how do they measure the distance of an object seen behind a microlensing event? Does the object causing the microlensing event change how they do distance calculation?
Yeah, good question, Craig. So how do they tell the distance when something, they're seeing it through gravitational lensing. So what Craig's referring to is that if you get a large mass between you and the line of sight with some really far away object you wouldn't normally see, the light coming towards you around that mass, the mass, like a star cluster or a galaxy cluster rather, acts like a big magnifying glass, and it bends the light path around, and it magnifies it but distorts it. And the degree of magnification, the degree of distortion, tells them how much mass is going on, which then tells them in turn how much gravitational lensing effect is going on, and tells them how to interpret their data. Now, I suppose I'm thinking ahead, would that interfere with the luminosity, and would they be able to then pull out, for example, if so things like, you're talking like really these far away cosmic things, supernova type 1As are sort of events. So I don't know if they can pick those up, but certainly you're redshifting, doing spectroscopy on these really far away galaxies. I've never seen any data around that, but I do know that they can pull the data out of those distorted magnified images and get a lot of information about the object behind it, as you're inferring, and the object in front, the lens, the mass. So it's just a good question. I can't look you straight in the eye and say definitely, but I would imagine with the spectrum, because they can tell how far away things are. In fact, I've just answered the question. You know that star, that most recent star, the furthest one away, Earendel? I think they've said it's that just announced this week that NASA's just spotted it with the Hubble telescope, and it's 12.9 billion light years away, just when the universe was only about 1 million years old. And whoa, how does the Hubble do that? The answer was pretty obvious as I read further down the article. Gravitational lensing. And it was from spectral analysis, the spectral redshift of that image, that gave them a redshift. I think the Z equals 6.2. Redshifts are measured in, they call them Z numbers. And it was a redshift Z equals 6.2. And that was done by the cosmic redshift and spectral redshift, and that was done through gravitational lensing. So that there answers your question. So I now can look you in the eye and say, yes, they can. Good question, Craig.
Thanks, Chris. I might just add to that when you're talking about microlensing, you're often interested in the foreground star because that's the one which is sensitive to planets or any distortions. And often another way of looking at the distance to the foreground star, the lensing star, is by using parallax. So some of these microlensing events are seen both from Earth and, say, from a space telescope like Spitzer, and the time when the light changes, so the time when the light is magnified, gives a difference in gives that parallax difference. So the maximum brightness that you get will be at a different time on Earth than it is from a telescope that's distant from Earth. So just add that one in as well.
That's good. I think I missed the question. Sorry, I didn't realize he said micro lensing.
Yeah.
I was thinking of gravitational lensing in general, but yeah, your micro lensing. Sorry, you're quite right. That's a very good explanation.
Another question from Paul this time. How do astronomers measure distances to black holes if they don't emit any light?
Yeah, I think a lot of it by their environment. That's unless you're looking, like your silhouette and stuff of M87 that was in the news a lot. I think the way you detect black holes is by looking at their environment, what they're doing to your environment. And they do know how the distance black holes are, and I would have thought you might need to have a quick Google on that one there, Paul. But I would have thought that the way that you, by first principles, the way that you observe black holes is by what they're doing to their environment, and you see that typically you'll often see stars, or whether you've got an accretion disk zipping around it, whether you've got stars zipping around it. You could then measure the distance to those particular objects and infer it from there. So I don't know if you've got any other thing to add to that, Steve, with your own knowledge, but that's what I would have thought.
Yeah, I think probably you can see the stars that are orbiting the black holes. So just by using the normal methods that you would for a star, such as looking at redshift or parallax, if it's close enough, that kind of thing.
Yep. So it's the effects that the black hole causes around its environment. So you look at the environment, not the black hole.
Keith, another one from Paul, actually. This is partially answered by you and partially answered by someone else on the chat, actually, who says, given that the universe is expanding, how do we incorporate this calculation into our data on objects outside our galaxy? Astronomers always present distances to galaxies as a fixed number.
Yeah, could you just repeat that? I just want to make sure I didn't quite understand the question.
I think he's talking about given that the universe is expanding, how do we incorporate this calculation into our data on objects outside our galaxy? He's thinking that if you say a galaxy is so many million light years away, obviously that number is going to be changing.
Yeah, so when you're looking back through distance, you're looking back through time as well. And you're looking at, so I hope I'm answering the question right, but they've got their supercomputers, they've got the cosmological model, they know at a set time. Remember the standard ruler, they go back to a set time and they know how quickly the universe was expanding with their supercomputers. And you've got the Hubble constant in there as well. That tells you the expansion rate of the universe. Now, whether that is expanding, how that expansion has changed over the history of the universe, they can roughly measure that. They're getting better and better at that with the Dark Sky Survey. But the universe, for example, started accelerating expansion about 4.5 billion years ago, roughly. So I think when they look back and see how something distance is, they put that into their supercomputers with their equations and allow for that, for the expansion rate. and they roughly know through looking back. That's another whole talks. I'm going to talk about that a little bit next month, and Jonathan talked quite a bit about it last month. So if you go back and look at last month's talk as well. Hope I've answered that question there, Steve. It's a bit hard when you're listening to a question to take it forward.
No, it is a little bit of a mixed one. Last couple of quick questions from Keith. Wants to know, has anybody repeated Hubble's work to determine if the Hubble constant is constant or changing over time?
It is changing over time. It's expanded. Most of the research with the Hubble telescope has been with these type 1a supernova. We're going to go the cosmic distance ladder, trying to calibrate with the spectral redshift, and then using Cepheid variables. And the evidence so far does show that yes, the universe expansion rate has been changing over and it's that's where they've brought in the cosmological constant back in again, where the expand is starting to accelerate. Probably in the last 5 billion years or so, it started to accelerate. It's no longer coasting along. In fact, when they did those studies, the two groups of scientists who did the studies in the late 90s, that discovered that, they were expecting to see the universe, actually the expansion rate still expanding, but the rate of expansion slowing down. Here you got that inflation went like that. And they were expecting the universe expansion just coasting along, but slowly slowing down. But about 5 billion years ago, it appears it started taking off again. So I hope that answers that one there, but we're going to talk more about the expansion of the universe and measuring that with accuracy next month. But I hope, have I answered that question reasonably?
I think so. And then the final question from Keith, which is another redshift question, is also, how can they determine if the redshift is all due to recession, or could there be reddening caused by intergalactic dust or dark matter?
And your Doppler as well too. The general consensus is, and someone raised a question a little bit with Jonathan last month too, the general consensus is that your spectral redshifting and blue shifting that you see from galaxies within our local group, most likely, is the general consensus, it is from the velocity, that there's no real appreciable expansion of space-time. It's more that they're traveling through space-time towards us. Now, there's all sorts of theories. Is space-time still expanding, and they're just traveling through the expanding space line, or does gravity trump a gravitational system like a galaxy cluster trump the dark energy that's separating that's causing the universe to expand? They don't know, and there's an argument about that. Different cosmologists say different things. But the general consensus is that the Doppler, or the spectral shifts, whether it be a redshift or a blue shift, within galaxies within the local group, is all through the Doppler effect. It is either coming towards us just traveling through space-time, in which case we're getting it blue shifted, or it's traveling through space-time without any appreciable stretching of space in the meantime. So that's Doppler redshift, as opposed to your cosmic redshift, which is the light traveling from distant galaxies, but as it's traveling through space-time, the space-time is stretching out those light photons. So yeah, that's they tend to that, as opposed to distinction and stuff. I think there's a little bit of reddening with that, but I think you're getting less and less of that as you get further down. But I've never really seen that being mentioned as something appreciable upsetting their data. The main comments you'll see in the literature is what's due to Doppler and what's due to cosmic redshift through expansion of space-time. And it seems to be the spectral changes we see within the local group are usually from Doppler. You can pretty much say, hey, that's from the Doppler effect. Like, for example, Andromeda coming towards us, it's blue shifted. Anything beyond that in the next galaxy cluster is going to be through cosmological redshift, through expansion of space-time.
That was a good explanation. Thanks, Chris. And that's it for the questions. So thanks again for another really informative session.
Thank you very much, Steve, and thanks everyone for watching. It's you guys that make us do all this. It's a lot of fun, and we'll see you in a month's time. Hopefully, well, either way, it's going to be recorded, whether it's me sitting in my home office or whether it's going to be in the Star Dome room. So either way, it'll be recorded. But we're going to talk about the cosmic distance ladder and how they know that they're getting it as precise as they can. And we're going to talk all about the Hubble constant and the expansion of the universe. So we'll see you then, guys. Thank you. Good night.